bit. All right. There we go. So anything from homework stuff? Okay, all right. You guys doing okay? We could be doing a lot worse. We could be in that room. So, okay. So just to kind of, first thing I want to say is there will be a quiz on Tuesday. On chapter 8. Just kind of run down some stuff in chapter 8. Remember what the heck we did. Review some of the major ideas. So for example, the final's coming up, right? So on the final exam, the major difficulty is going to be figuring out when to use which formula, because I'm going to let you have the formulas on the formula sheet, right? You're going to have all those. It's just going to be a question of when do I use which one of these? The only formulas we have that have a plus or minus in them are the ones for constructing confidence intervals, right? Because that's the whole idea. We get an estimate and then we kind of go out away from it a little bit. Hey, all right. You're my first test subject about the map. All right, good. So on a quiz or a test, for example, this next quiz is going to be easy because it's all confidence intervals. But on the final, if I say create the 90-something% confidence interval, you know it's going to be one of these three formulas. Right? If I say find the or create the 90 whatever % confidence interval, it's got to be one of these three. This one is the most obvious one. When do I use this one?
You don't have a standard deviation?
No. What's this one all about? What's that represent? What's p hat represent?
The probability of success?
Okay, sure. It's a percentage. Right? So if like 78% of the population likes to watch TV, that would be the percentage of the population. That's the probability that I pick somebody that likes to watch TV. So those are the same thing. So if I ask you, create the 95% confidence interval for the true percentage of people that like to watch TV. Okay, percentage, this guy. They give it away, right? When do I use a t-score? The formula tells you. When would I use a t-score instead of a z-score?
When you don't have sigma.
Yeah, if I don't have sigma. So I don't allow you to use notes on a test, right? Because I'm a math teacher, we're all jerks. But I do let you have formulas, and they are notes. This tells you I use a t-score when I have only S. I'll use a z-score when I have the real standard deviation of the population, right? What else has to be true, though? What's the very first thing I check to even make sure I can create a confidence interval in the first place? Is it normal? I love it. Okay, now. There you go. When I have a problem about means, this is old news. Central limit theorem stuff, right? Chicken, lettuce, tomato, CLT. When I have means, what do I need to check to make sure it's going to be normal enough?
Greater than 30.
Yes, n greater than 30. For a percentage, though, it's not good enough to have a large sample size. And again, I really, really want you guys to get this idea. Yes?
It'll just tell you that it's a normal distribution.
No.
Damn.
Good try that. I don't know if you remember. So if n times p, what was n times p the formula for?
The mean.
The mean. If that comes out to be small, so if I have 1,000 for my n, that's way bigger than 30, correct? But what if my p is 0.001? What is 0.001 as a fraction, real quick?
1 over 1,000.
Yeah, tens, hundreds, thousands. So 1,000 times 1 over 1,000 is freaking 1. Yes? Where would the highest bar be then? If I draw this histogram like we had on that one sheet,
That one.
it would be at 1. So do I have enough room to go up and come down and actually look normal? Does that look normal? Where's the peak supposed to be in a normal curve? In the middle. So I desperately always want every damn thing we do to actually make sometimes physical sense, which is neat. But in order for this to maybe be normal, to have the mean has got to be far enough away from that wall, so it's got room. So if I have the mean more in the middle, then it's got room to kind of build and then come back down. Now that looks a lot more normal. And that's where this comes from. NP hat greater than equal to 5 NQ hat. I can't remember if this book has an equal to or not. It's funny, each book is a little different. Are you guys semi with me? Right, this was the idea about the alternate universe Florida, where if they get the sample size big enough, everybody should be close to the middle and it becomes kind of nice and normal. This one is that idea. Get away from the wall. This one gets it away from this wall. This one gets it away from that wall. So together they sort of say you've got to be somewhere in the middle so you got room to actually go up and come back down. It's kind of a kick-ass idea, right? It's actually got a visual, physical interpretation. Okay. So these are the big three. Those are the big three. There's a little side note about what else you got to check before you can use them. And then you got 2 more formulas from chapter 8. And these are the formulas that are like, how large of a sample would I have to take to be within 1% or to be within 2 millimeters of the true length, right? The true mean length. That would be solved for n. So if I ask you how large of a sample do we need, I want a formula that says n equals, because n is my sample size, right? So again, you guys love coming with me along on these derivation ideas. I give you the alternate universe Florida, all this weird shit. We talk about the concepts. Once we've talked about the concept and we constructed a formula, I can give you shortcuts. Some like key things to look for. If it asks how large a sample do we have to be within whatever, I want to use something with an n in it. If it's talking about a mean, I want to use this one. Or you can write it like this. And again, we derived that formula, but now that we've derived it, it's a formula, it's a tool you can use. And when do I use it? When the question is, how large of a sample do you need to take to be within blah, blah of the real mean? For the percentage, I obviously want a formula that's got percentages in it. And that would be this guy. So these two accomplish the same thing, just this one for means and this one for percentages. Now, a really good question somebody could ask. How many formulas do I have for the mean for a confidence interval? 2. One of them has a t-score, correct? So you could, it shouldn't be too big of a surprise. If I have t-scores, this formula would become this. T instead of z, s instead of sigma, and then divided by the error. It's the same formula, just with the correct values in there. Okay. Maybe? Okay. Oh, there it is. I left my water bottle at home. Yay. Okay. So any questions on that? That's chapter 8 right there. Some of the problems give you confidence intervals that they already figured out. Right? There's a few problems like that. So if I said, if I said I created a If I created a confidence interval for the percentage, and I got 32% up to 40%. So that's the confidence interval I created. Can you figure out what p hat was? Where is p hat in the interval?
In the middle.
Must be in the middle because I start at p hat and I go up and I go down the same amount. So what score is right in the middle of those two? 36. Right? Now the error is how far away I am on either side from the middle. So if the middle is 36, obviously the error must be how far away is either one of these from this? 4. So the error is 4%. So you will see, I think it's like 3 problems or something, where they give you a confidence interval and they ask you, what's the, by the way, I always forget to say this, X bar and P hat, the book calls them point estimates, which is just a highfalutin way of saying our best guess. It's the estimate for what the actual mean or the actual percentage is, but it came from a sample, so it's just an estimate. So if you see the words point estimate, that either means P hat or X bar, depending on which kind of problem you're doing. Okay. So so that's chapter 8 in a nutshell. I think last time we finished that T-score worksheet. Is that correct? Did everybody get that, by the way? Anybody need that T-score? Yeah. You're gonna be excited about this day. You got a whole new chart. Whole new chart. Let's see. Okay. New projector. Who it is? Okay. Here it comes.
Should we just one of the lights so we can see better or anything like that?
Yeah, I'll think about it.
Okay.
Sorry. Yeah, I'll turn it off here in a minute. I'm going to use that in a minute. I just want to get him up and going. I also want to make sure, let me see. Everybody got their T-score charts, right? You got that?
Yes.
Okay. So let's do a couple of, let's do one together to make sure everybody remembers how the hell this chart works. Shoot. Oh, crap. It's a new thing. Let's see which one. Which one is it? Okay, let's see what happens. Okay, not that one. This one. Yes, okay, cool. Ooh, look at that. By the way, I do kind of wish this could be our room, but there's a class in here on Tuesdays. So just to remind you guys, this is the T-score chart, but what's at the very, very bottom? Z-scores. And why does that make sense? Again, T-scores were invented for when we don't know the actual standard deviation. So their job is to increase the size of my confidence interval, because the whole idea of a confidence interval is I catch so much shit and then I'm that confident I caught a certain thing. In this case, the real mean or the real percentage. If I'm not sure how spread out things are, then to cover my ass for that fact, the interval should get a little bigger, just to be a little more conservative. Does that just make physical sense? So the smaller my the smaller my sample gets, the bigger the T-score gets. Why does that make sense? Because the smaller my sample, the less certain I am about the standard deviation. I've got to cover my ass even more. Right? Is that right? So as you go up, T-scores increase in size. Because as I go up, this is not really the sample size, but this roughly is the sample size. The sample size gets smaller. So I got to cover my ass more and more and more. So instead of going out 1.96 like a Z-score would have me, I might have to go out 2.03. Just a little bit more, just to be more conservative. You guys semi with me? Okay, I like how some of you guys in your eyes, you're like, I have no idea, but you're nodding your head. I like it. Okay. The other really nice thing about this chart, so this chart is a t-chart, but it's also got z-scores. So basically, this is my go-to. Unless I give you something that's not on here. Could somebody tell me what this means right there?
90% confidence.
90% confidence, because that means directly 10% in the tail, so there must be 90% in the middle. That's a 90% confidence interval. Today, we might start to go in the direction of understanding what the hell this is doing here. Right now, we don't need this, do we? Pretty soon, we will. But right now, confidence intervals, you could always look here. That's 98%, so that's 2% outside. 80%, which is a sucky confidence interval, but oh well. Okay, maybe. Sucky is a technical word, by the way. Okay. And of course, if I only have so how big of a sample does this represent right here? 7, because the degrees of freedom is n minus 1. And I tried to show you that example about where the idea of degrees of freedom comes from. In fact, so I showed you, remember I showed you an example where we knew 3 numbers averaged to be 10, and the first 2 we could totally make them up, and the last one had to be something specific. So what this does is it says we have all the data except for the one data point that would make the sample mean become the real mean. So that's where the n minus 1 idea comes from. If you really don't understand what I just said, it's okay. But it's sort of like, because we don't know what the real mean is, we're missing one data point that would make the mean become the real mean. And that's why it's n minus 1. We're assuming we're missing that one magical data point. Okay. But all you have to remember is degrees of freedom is n minus 1. Okay. So let's try an example out. Let me see. Do I have paper? Paper. Yes. Do I have a pen? Maybe. Sure, I'll use this. So let's say I have a situation where n is 37, sigma unknown, and I want to make a 98% confidence interval. My first question is, what do we use? Zort, Z or T?
T.
Why do we use T? There are 2 things I need to hear from you. Why do we use a T-score? Somebody give me one thing.
Sigma's unknown.
Yeah, I don't know sigma.
Not normal? Or
Say again?
is normal, like, we don't know if it's normal or not?
We do know if it's normal.
Oh, yeah.
In fact, it must be normal for me to do anything. So we're in stats 1. We can't do shit if it isn't normal. Stats 2, you learn some stuff to kind of work around that. And unfortunately, guess what? We don't teach stats 2 here. And some of you guys are like, that's fine, Jeff. But I don't know sigma, but I can't do a damn thing unless it's normal. Why do I know this would become normal? Why would I know the sample means would be normal?
30.
N is bigger than 30. I love it. So Z or T, 1, N is bigger than 30. It's normal enough. I could do something. 2, I must use T, sigma unknown. And let me be a little more specific. Let's say that we know S. We got to know some kind of standard deviation. S known. There we go, John. So can you guys take a minute? And again, if you haven't used the Z-score, the T-score chart yet, just hang out. Take a minute. Don't say anything. Find the appropriate T-score for me. And of course, don't forget, you have to know what this is. All right. So this is your note or you don't know at the moment. So what's the degrees of freedom?
36.
36. What's alpha?
0.02.
0.02. All alpha is, it looks like a little fish dude. Fish dudes have little tails. Or dudette, I don't know. I don't know the biology of a squiggle fish. But fish have tails. So it's the area of the tail. So 90% in the body, there must be 2% in the tails. So I know to look at 0.02, two tails, 0.02, and I know to stop at 36. What'd you guys get?
2.4.
Yeah, 2.434. So the way this chart works, if I stop, I get a t-score. If I go all the way to the bottom, I get a z-score. Kick ass. Okay. So t would be, what did we say, 2.434?
Yeah.
Sorry? Yeah, okay. So what if somebody came along right when I was about to do this and they said, oh yeah, by the way, I know what sigma is. I know sigma is blah, blah, blah. They tell me what sigma is. Same situation. But now somebody comes along and says, hey, I know what sigma is. What can I then do? Yes?
Just go to the bottom of that column.
Yeah, because now I can use z-score. So I would still use this chart. So I'm going to go to 0.02, two tails, go all the way down to the bottom, 2.326. So z would be 2.326. So the t-score will always be a little bit bigger or maybe more than the z-score is, because its job is to cover my ass a little more because there's something I don't know. I don't know how spread out the data is. Okay, maybe. So let me give you guys a problem to try, a full problem. Let's say we look at what do you got, Jeff? I don't know, Jeff. 51 textbooks. We find a mean of what makes sense? $142 with. Am I showing out of touch I am? Does that sound about right? With a standard deviation of pretty big probably. $38. Of course, you guys are in my class. You don't have to pay a damn thing for your book, which is the way it frickin' should be. But oh well. Blah, blah, blah. So I want you to please construct. So we don't know what the actual mean textbook price in the bookstore is, but we took a sample of 51 textbooks, and that's the mean and standard deviation we found. I want to construct a 99% confidence interval. Make the 99% confidence interval. Okay. So you really just do exactly what we just did, and then you use the correct formula up here to plug stuff in, right? The one thing you really have to work to get is the z or the t-score. Oh yeah. Thanks. If you need to borrow a calculator, as always, just do it. Yeah, Nick.
Because you know this is like 99%, you want us to use like the t-score? Do you want us
Not
to
because of the 99%, but I would use that chart. Yeah, okay, I see. Okay, so if I give you a percentage that's on that chart, like 98, 99, 95, 90, 80, use that. If I said 96%, that would be me being a little evil. You'd have to use the z-score chart.
Oh.
Right, that one's only got so many columns.
Okay.
Yeah. Cool. Make sure it's got good battery. I think they're all good. But I really, on a different level, I want this. We took this sample, correct? We got a mean of $142. Is that the actual mean of all textbook costs in the bookstore? Hell no, right? That's just from a sample. So this idea of constructing this interval should hopefully just intuitively makes sense. That 142 is more than likely wrong. So I have to get some kind of idea of what it looks like it is. And that's what this does for us. If I say $142, I'm like, how far off do you think you are? Well, we can calculate the error. We can see how far off we think we are. That's what that formula does for us. Are you guys using Z or T? T. So what I'll get is somebody will tell me, I know the standard deviation, so I'm going to use a Z-score. Why does that not make any sense? The phrase, the standard deviation, does not make sense. Because how many standard deviation types are there? 2. So is it the population standard deviation or is it the sample standard deviation? In this case, that came from the sample, correct? So the textbook is not going to say, and I'm not going to say, this is a sample. No, you got to go, we took a sample and we got the, okay, that's the sample standard deviation, T-score. Why am I allowed to do anything? Sorry.
Would there be questions where it says like, oh, we took 51 out of here, but there is a known standard deviation?
Oh, hell yeah. In fact, that's 8.1. 8.1 is, we know the actual population standard deviation, which happens. You take like a, normally that's if I'm taking like a subset of a population, so I know the population standard deviation, and I just take a subset, so I get a sample mean, but I know the population standard deviation. In most cases, in some kind of statistical analysis, we don't know shit. So we got to get an estimate for the mean and the standard deviation.
So anytime you see like, oh, like a sample, automatically use a T-score?
Yeah, if, in general,
Yeah.
if you're like, what kind of standard deviation is that? It's a sample standard deviation. Because they would have to say, either they would say population standard deviation, or they would say the standard deviation for all textbook prices is, and that's a sample. That's a population standard deviation,
So
all.
Z-score, look for population and all.
Yeah, look for something that tells you it's the standard deviation for everything, the whole
Okay.
population. T-score would be basically
You can't
everything else. So if you're like, I don't know which one it is, it's a sample.
Okay.
It would be really clear if it was a population, yeah.
Okay.
Okay, guys, help me out. All right, I'm sorry, I mostly talked there. If you guys don't tell me what it is yet. Did you guys look up the T-score yet? What's the degrees of freedom? 50, right? Is that cool? N minus 1. What's alpha?
0.01.
0.01. So now I know which column to look at, and I know where to stop. So now you can look up your T-score if you haven't done that yet. 99% confidence, so it should be kind of a bigger one, because I got to go up farther than normal. So if I look at the 0.01, and I stop at 50, I get 2678. Is that cool? So now we got everything we need. What's X bar? 142. What is S? 38. So now I just got to plug and chug. You guys have all heard that phrase before, right? Plug and chug? Have you heard that phrase? No? No. Okay, so probably one semester I had a student and look at me like, what the hell are you talking about? So plug the values in, chug the answer out, right? So plug and chug.
I thought that was
Huh?
I did not think that's what that was going to be.
I got you. There's nothing untoward. It's just plug and chug. So I know every value I need for the formula. Take a minute and try to get the confidence interval. All right, let me catch up to you guys. 142, give or take. 2.678 times 38 divided by the square root of 51. And again, it's a really common mistake to put the degrees of freedom here. If you do that, I'm not going to take points off because we're all human, but it's got to be the full ND there. And as always, my suggestion is to calculate the error first. Especially in the homework, because sometimes they'll ask just for the error. So you might as well calculate that sucker. So 2.678 times 38 divided by square root 51. I get 14.25 roughly. That's nifty. Is that what you guys got? So then I have to do 142 minus 14.25 and 142 plus 14.25. Now, obviously, I did not just go to the bookstore. I did not just take 51 textbooks, so this is made up shit. But let's pretend like I did. If I've got $160 and I go to buy a textbook, should I feel decently confident that I will be able to get my textbook?
Yeah.
Yeah, because 160 is more than the highest level of my confidence interval, right? Are we certain we'll have enough money? No. Because what's the probability that it's actually it's not in here? 1% chance. Which, a 1% chance of being wrong is pretty good for me, so I feel pretty good about that. Okay, maybe. Is this? Yes, okay, all right. So, I mean, there's a lot of concept in statistics. I don't know if you've noticed that. But then you get to the nuts and bolts. We just have to know mechanically, how do I find this? And then once you got everything you need, you just got to put it into the right formula and just crank it out. I don't like to teach that way. I want you to understand where the hell these things come from. But then at this level, it's just, how do you tell what's the right formula? And then how do you get the stuff to put into it, right? Okay. So, before you think we're not going to do it, take a minute and write the conclusion. What is our conclusion? Let's see, who's got that? We are 99% confident that what?
127.
The interval?
Yeah.
$177.75 to $156.25 contains the true mean, or you can say population mean textbook cost. Okay. All right. I try to make it as concise as I can because I don't know if you noticed, I don't like to write too much either, but this is important. This is probably the most important step, is interpreting what the hell you just did. Right? And again, some of my colleagues do you could actually do everything we just did in the calculator. And some of you guys are like, who's that? Let me go take that. But then you don't learn shit. It's all just numbers. So I personally, that's why I do make you do all this work, but maybe I'll consider showing you how to, well, let me show you. Let's see, watch this. If you hit stat, We've done edit, which is where you can sort, you can put the data in, correct? We've done calc, which is where we can do one variable stats and stuff. But we haven't looked at tests yet. So if you go down, look right here, T interval. Do you see that? So it tells me, do I have a list of data or do I want to plug in the stats? So I can plug in the stats. So let's see what this does. X bar was 142. The standard deviation was, 38. N was 51. Confidence level 99%. Calculate. There. Isn't that the same thing we just got? Right? Now, I totally understand. From some students' perspective, they'll look at me and say, "What the shit, man? You got the answer, man. You made me do all this shit, man." All right, I don't care, right? I don't, because I know you're here to learn, and this doesn't teach you anything. It all happens in the black box of the calculator. But now you know how to check your freaking work, which is always nice. You with me? So I've had students in my stats class that said, "I took stats last semester, and my teacher let us push buttons." I'm like, "That's great for them. It's not me. It's too damn bad." Right? And maybe that's why you're here, because you didn't understand what you were doing, because it's all in the box. Okay, I'll stop. I'm sorry. So I do like to show you how to use this very expensive calculator to at least check your work, right? Okay. Blah. So, any questions from that section or that chapter? Before we move on, we're gonna move into the next chapter now. Okay, all right. By the way, did I put it up here? Yes. So we do have that quiz next time on all of chapter 8. I'll put the formulas on the quiz again. I like to put the formulas on quizzes, and then you guys have your formula sheet for the test. Just makes it easier on everybody. Okay. So, I want to talk about something a little more interesting. We keep talking about freaking average age and stuff, and that's getting kind of boring. And I know some of you guys are like, that's not the only thing that's boring, but let's do this. Does anyone have, I'm not going to show this data, so don't get freaked out. Does anyone have an idea of what the average grade in this class is right now? Anyone have like a feeling?
78.
All right, 78. Both of you said 78. That's kind of funny. So I've got somebody thinking that the mean is 78. Does anyone think that's wrong? Come on now. Does everybody believe it's 78?
No.
Okay, you think it's wrong. In what way do you think it's wrong?
It's probably not a whole number.
Oh, okay. Does anyone think it's higher or lower than that? It's okay. We're not going to look at the data. Don't freak out. I'm not going to say you're wrong. What's wrong with you? This is just an example of what we're about to get into.
I'm going to say it's lower.
You think it's lower? Okay, so there's an accepted mean of 78. I have a claim that the mean is less than 78. Okay. So this is not the best example, because is the population very big? No, but let's say that you're only going to talk to a few people. So you're going to take a sample of people. Are you with me? I really want this to make sense, because this, okay. I mean, I want everything to make sense, but. So we have kind of an idea that it's 78, and then we have a claim that it's less than 78. If we take a sample, and I get, let's say I take a sample and I get 77. Is that conclusive evidence that this claim is correct? You could do this. Why not? Why isn't that good enough?
Because whenever you're using a sample, you're missing one data point.
Yes, if you take us now, so I really want, everybody understands this idea. We're just gonna apply it very directly now, and we sometimes lose sight of this. Whenever we take a sample, the data, the actual numbers we get are not gonna be the real population. Of course it isn't, because there's gonna be natural variability. I could just pick a few people who happen to do really well, or in this case, worse, or whatever, right? It's just variability in the sample. So real quick, Ryan, if his claim is true, any sample we get, shouldn't it be close to 78? The sample mean should be close. If you're right, I'm sorry, not you, sorry, Ibudu. If you're right, if the mean is 78, you think it's less. If the mean is 78, any sample we take should be in there. Does that make sense? Okay. Because again, so if I get a sample mean of 77, that is most likely not good enough evidence, because a sample is going to naturally be a little different than the actual mean. So what are you hoping? And then you're like, why did I open my mouth? What are you hoping to see to prove that you're right? Not just a number that's less, but a number that is a lot less, right? I've got to be so much below 78 that it's evidence that 78 is wrong. So if 78 is the real mean, this is what the picture would look like. That means that most samples would be in here. If we got a sample that was out here, do you guys all just right now, this is a really surface level discussion, but this is the idea behind what we're about to do. If I get a sample right there, that is evidence that the mean really is less than 78. That is evidence that supports your claim. Does that make sense? So just being less doesn't mean shit, because we just took a sample. A sample could be wherever, but it should be close. So if I get a sample and it's way the hell down there, that is evidence that that's right. If I take a sample and it's right here, is that evidence that this is right? Nope, that's not good enough evidence. Okay, let me stop for a minute. That is, I said I'd stop for a minute. I always say I'll stop for a minute and then I start talking right away. That is the idea behind what we're about to get into. There are 5 steps to this process we're going to do. When I was taught, there was 8 steps. I've got it down to 5 steps. This is not a program, by the way, right? It's not a 12-step and then I made it 5 steps. This is just the process. There's 5 steps to this process, okay? And what this process is called, what we're doing is we're testing this out. We're testing this. This is a hypothesis. So we're testing hypotheses. This is a hypothesis test. This is what we're about to do. So in a hypothesis test, it makes sense that there's got to be kind of a general feel and an actual specific claim. There's got to be 2 parts to get us started. Does that make sense? So somebody says, oh, we all know that the mean is 20, and you're like, we all know that the mean credit card debt is $890. Like, no, it's way higher than that now. After everything we've been through, it's higher. So there's an accepted thing, an accepted statement, and then there's a claim of how it's different now. Okay. So there's what we call, this should be fun. I think this book, wait, is this book, every stats book is different, and I always forget this one. I want to use the right symbols. I think this one uses, yes, okay. So there will be one claim we'll call the null hypothesis. Heretofore affectionately known as the HO. The symbol is, yes, I did just say that. The symbol is called not. It basically means like the beginning. You can think of it as like O for original or something. Right? It's the stuck in the mud, the old way of looking at things, and then we come in with what's known as the alternative or the alternate hypothesis. heretofore known as the ha. So we got the ho's and the ha's. But do you see how naturally that makes sense? There was this idea, and then there was something saying, no, I think it's different. There's an alternate to that. Okay, maybe. Okay. So that's the beginning. So, for example, oh, by the way, before I erase all this, I think you guys all get the idea of this picture. It looked like you got this pretty well. What needs to be better defined in terms of what I just said? So I said, if the mean really was 78, we should find something that's close to it. If something's really far away, that would be evidence it's less than 78.
On there, it'd be, I would want like a better defined scale.
Okay.
How far away.
More important than just the scale, though, is kind of related to that, but like, what is this?
Your interval?
What is far enough away, right?
You need to know the standard deviation.
Yeah, it's based on the standard deviation. Because 77 could be really close to 78. Is 77 close to 78?
Depends on the content.
Now, I love it. Of course, we're humans. We're going to say, yeah, 77 is close to 78. What if the standard deviation is 0.1? How many steps is it from 78 down to 77? 10 steps. And we should all right now be fully aware that a z-score of -10 is stupid big, yes? That's like somebody who's 2 foot, tall versus the average, yes? Jeff, you're the average, okay. You guys kind of with me? Okay. So, yes, exactly. It's based on the standard deviation of the situation. It's also based on the size of the sample that we pick. In fact, we're going to kind of borrow from the confidence interval formula the same idea for standard deviation, sigma over the square root of n. So it's all about, how do I define what far enough away is? Okay, I like it. All right. So we got this idea that gets us started. We have some situation and we have a claim about that situation. The null hypothesis, this guy, will always include an equals. So it'll either be equal to, less than or equal to, greater than or equal to. And the reason is, I want that guy to be the stuck in the mud dude who thinks it's in here somewhere. So it's always got to include this number, the accepted mean. It's always got to include that. I want the other guy to be all about getting far enough away. I want him to have a greater than, a less than, or a not equal to. Now, real quick, let me show you something about, remember the t-score chart has these weird 2 rows at the top? And we're normally only concerned about one of them? Ryan, sorry. Which side of this picture are you most concerned about? Where do you want things to happen?
The left side.
So is this a 1 or a 2-tailed test?
One tail.
1 tail. There, that's why we need that up there, right? I'm going to make a better connection in a minute, of course. We've got to see what the shit does that mean. But now I just want you to, on the surface, just go, okay, that's why it's got 1 tail, 2 tail. What if you had said, I don't think it's 78? What does that mean? I don't think it's 78. So it could be either less or greater. That would be this situation. I don't think it's equal to 78. That would be a how many tail test? 2 tail, because then it would be either side would be evidence for me. So if I thought it was greater, it'd be a right 1 tail test. If I thought it was less, it'd be a left 1 tail test. If I thought it's not equal to, I don't care which side it is. They both would be evidence for me. Okay, maybe. Okay, I like it. All right, so this is going to be step 1. It's going to be figuring out what the ho and the ha is. And I might as well say this. If we get a sample far enough away, what is that evidence? Who's wrong in that case? If I get a sample way out here, if Ryan got a sample way out here, which one of these people is wrong? Which one of these people is that evidence they're wrong?
It would be evidence that the old one is wrong.
Say again?
That the old one is wrong.
Yeah, the hope, right? Hopefully everybody's cool with the language. If you're not, too damn bad. So if we get far enough away, we can reject, okay, you really love this, the hope. We can support the ha. I really just want that, and again, this is just formalizing the language. If I get so far below the supposed mean of 78, that is evidence it isn't 78. That is evidence against this guy. I can reject this guy. I can support this guy. Support Ryan, right? Okay, Ryan's like, sounds good. Please support me. Of course, everybody's like happy about that, but his claim is it's a lower average. But that's okay, we'll move past.
I'm only now realizing that this scenario makes me the hoe.
Exactly. There you go. It's good to know. It's just, the more you know. Do. All right. I love it. Evaluation. My teacher called me a hoe. Okay. All right. That's step one. Step one is this. Step two is going to be involved in defining what far enough away is. Well, I'm sorry, that's step three. Step two is going to be, can we even do anything? So what do we have to check? So this is step one. What do we always have to check to make sure we can actually use the distribution to do stuff? We have to know if the situation I'm looking at is normal. So step two would be, can we use Z or T? Okay, so Zort. Right? So if it doesn't say it's normal and N is less than 30, we're screwed. We actually can't do anything. I would never put that kind of problem on a test because that would suck. Because you would do a lot of work if you just missed that you didn't have to do it. That would be really evil. And I'm not that evil yet. Give me a few more years. All right, how are y'all doing so far? I mean, this.
What did that say on number 2?
Can we use Z or T?
Oh,
But I just make it Zort.
okay, I just got confused.
No worries, I understand. Okay, so let's do this. I've got a handout. We're going to kind of step through it. And if I were you, as we do chapter 9 homework, I would have this handout sitting next to me, because what this handout does is it fully explains every step. We've done the first two. I want to kind of give us a more structured problem to look at for the next two steps, or next three. Okay. So I want you to read through this real quick here at the top. Read through the situation. Something near and dear to all of us, the lifespan of the northern Minnesota coyote. We're all constantly thinking about this, so I figured we'd talk about it. So, don't start looking at the steps yet. Don't worry. And this is from an old textbook. I got to make this because some textbooks use the hose and the highs. This one uses the hose and the ha's, so there should be a little HA. Okay. But just the idea of it, does it make sense? So does his claim even kind of make sense? I mean, if we have creatures in captivity, they're going to do worse if they have less room. Yes, especially things like elephants. So thank God they gave the elephants more room, right? Stuff like that. So normally most animals are going to need more room to be better. In this case, he's talking about lifespan. So he thinks, his claim is that they'll live longer if they get more room. So the mean lifespan in captivity is 10.15 years. He takes a sample that of coyotes that died, but they had more room, and he finds a lifespan of 12.45 years. Can we just stop right there? Well, I mean, isn't 12.45 bigger than 10.15?
Yeah.
So can we just go, screw your 5 steps, Jeff. It's freaking bigger. Leave me alone. Why is that not good enough? He just took a sample. I don't know. It could have been naturally. He could have just accidentally picked a lot of coyotes that were going to live longer no matter what. So, does that? Okay, so that's why we have to do the steps. The steps guarantee that the amount of evidence is correct, that it's enough evidence to show. So we can do the first step. What is the claim that somebody is making?
12.445 is greater than.
No. Okay, so, not your fault, Sophia. The weird thing about a textbook problem is you're going to get all the information, correct? How does this work, though? Do I take a sample before I make a claim? Or do I make a claim and then I go see if the sample shows my claim? In reality, we have a claim and then we go get a sample to check it, correct? This number will never show up in this because this number is from the sample that we're going to take later. So somebody has a feeling about the reality of things before they take a sample. So what is the feeling they have?
The trimming should be higher than.
Yes. So let's write that in mathish. There's a claim that the mean is more than 10.15. And we understand that's the mean for the sample he's that's the mean for, not the sample, but the population. The mean for all coyotes that are given more room to run. Or excuse me, northern Minnesota coyotes. I really hope the northern Minnesota coyote exists. I think they do. I think I looked up this data a long time ago. So, is everybody with that so far? I mean, the claim you can normally find pretty easily. I think it lives longer. I think it's less now. I think it's different. I think it's the same. You're going to be able to find the claim relatively easily. The null has to have these symbols because it's got to include the middle. The alternate has to have these symbols. So the claim we just found, where does it go? Does it go next to the ho or the ha? Yeah, it doesn't have an equal sign of any kind, so it goes by the ha. Now this example was a little bit different. I was just trying to get the idea out there. But whatever these are, they must be opposites. So if that's the ha, what's the ho? The opposite of greater than is less than or equal to. So, okay. We can tell right now if this is going to be a 1 or a 2-tailed test. In fact, the tails, since this is the guy that thinks it's in the middle somewhere, this is the guy that's going to tell me what side I want to find a sample in. So is this going to be a 1 or a 2-tailed test? Where's the tail going to be, right or left? Right. In fact, the little symbol is an arrow. So it's going to be a 1-tailed test, and it's actually going to be up here. So in order to show evidence that the mean is actually bigger, I need to find a sample that's way up here. And again, we're going to get to the point where we define what far enough away is. That's a key part of this. And you notice I tried this sheet. This sheet's going to be a lot more explanatory than normal problems are going to be. So everything in black is kind of like the idea, and everything in red is, well, in black it's kind of like the nuts and bolts, and in red it's sort of like the idea. So can we use z-scores, t-scores, or nothing? So 2 things we got to look for, yes? Okay, what's one of them?
The sample is bigger than 30, so you know it's wrong.
Good. So one of them is in a normal distribution. So either it says it is, or the sample size is big enough, right? Somebody else tell me what's the second thing that's going to tell me which thing to use.
Population.
Yeah, n is 41, bigger than 30. Check. And we know which standard deviation do we know?
Z.
No, I mean which standard deviation do we know? Sigma or S?
Sigma.
Which one do we know?
Sigma, right?
Yeah, sigma. Okay, I just couldn't hear you. Sorry. So that tells me I can use a z-score. Not a big deal. Again, use a t-score if it's normal and I only know s. Use a z-score if it's normal and I know sigma. Right? T-scores were invented to cover my ass when I don't know sigma. Okay. So now this semester, I remembered to talk about this symbol early enough, so now we're not freaked out about it. So here's the idea, and this is why I used this language just a minute ago. If the sample makes it far enough away, and again, there's going to be a lot of steps, there's going to be a lot of work, there's going to be a lot of doing stuff. Keep in mind what the idea is. If my sample is far enough away, I can reject this guy, because this is the guy that thinks it should be in here. If I get freaking far away from this, then I can reject this guy. So that's why I call this the rejection region, right? Now we already defined where it's going to be. Where's it going to be? We already defined where it's going to be, right?
Alright.
We already drew the picture, so it's going to be up here. And what's alpha mean? What's alpha mean? It means the same as always.
It's the tail, right?
Yeah, the area and the tail are tails. In this case, it got one tail, so this is all 0.01 right there. Can you guys take a minute? Don't say it out loud. Find the z-score for this.
Z-score chart?
If you want to. I would use the t-score chart.
T-score, right.
And I always get somebody who's like, why would I use the t-score chart to get the z-score? Because, well, we'll see. In fact, there's the little thing for you there, Nico.
Oh. Oh, thank you.
So 0.01. Now be really careful. How many tail test is this?
41.
It's a one tail test, so I gotta look here, right? Don't look here. It's a one tail test, I look there. So this chart is constructed for hypothesis tests. We used it for confidence intervals because confidence intervals are always two tails, but now I see the real general idea. If I have a one tail test, I find the alpha here. If I go all the way to the bottom, I'll get my z-score, 2.326. Okay, so part of what this does, you guys remember back in the day when we first talked about unusual? How far away did it have to go to become unusual? How many steps did it have to go out? In fact, I just told you.
Outside of deviation of intervals.
To become unusual, I have to go out 2 steps, right? You guys remember that at all? The mu plus or minus 2 standard deviation? So what this is doing is, it's saying, okay, 2 is nice, but I want to be more specific. In this situation, unusual starts at 2.326. In fact, what I really want you to understand is, what the hell does that 0.01 mean? That means, dang it, I can't see the whole thing. If the mean really is 10.15, then there is a 1% chance that a sample would show up in here. Let me say that again. If the mean really is 10.15, there is only a 1% chance that a sample would show up here. So if I get a sample up here, what's more likely? The mean really is 10.15 and I just did something that had a 1% chance of happening, or the mean is actually higher? What's more likely is the mean is higher. It's only a 1% chance that the mean is correct if I get a sample that's in there. So it's more likely the mean is wrong. It's actually higher. This whole thing should shift up. Let me say that again. This area is the probability that something occurs in here. Is that cool? I mean, that's the idea since chapter 6. So there's a 1% chance that something will happen in here. If I get a sample that is in there, it was so unlikely to do that if this was the real mean, that what's more likely is this is not the real mean. That's evidence for the mean being bigger than 10.15. It's evidence for this guy. It's evidence against that guy. Okay, maybe. So how do I say this in words? Okay. And I really, you gotta, there's 5 steps to this. Each step is actually old news. It's just kind of like repackaged a bit. So, do I have a z-score up here already somewhere? Is there a z-score up there already written down? What is it? 2.326. What we're about to do on the next step. So what we just defined is what far enough away is. That is far enough away. So if I get a sample further than this, that's evidence that the null is wrong. Okay? So we just defined what far enough away is. So of course, what's the next step? How far did our sample get? We define what far enough away is. The next step is going to be, how far away is our sample? We're going to calculate the z-score for our sample. Yes?
So, if it's on that side, like, is there a way to find the other side? Like, would there ever be a problem where if it's outside on the other side too?
Yes, that would be a two-tail. So if the claim would have been, I don't think it is 10.15 years, then greater or less than would have been evidence, right?
So this is the same thing, but just one side.
Just one side, exactly. Which is why we have the one tail and the two tail option on the t-score chart, because it really is built for hypothesis tests. So what I do, since everybody agrees we have a z-score here, right? And actually I'm really happy I just remembered this, because I always forget. What the book calls this is the critical score. Because the book is weird. But the book calls that the critical score. Once you get past that, that's evidence of something. So it's critical. That's a critical score. So it does make sense. Okay. And they call that, they don't call it the rejection region, they call it the critical region. But to me, rejection region makes more sense because if I get in there, I reject the hope. Which is, a great phrase. Okay. So, what do I mean by put it into words also? I mean this. I'm about to calculate a z-star from my sample. Z-star represents where my sample is. So if z-star is greater than 2.326, what can we do? If my sample shows up greater than 2.326, what does that mean? What does it mean? Who looks to be wrong in that case? Go ahead.
If z-star is greater than 2.26, then the hope is wrong.
The whole is wrong. I love it. So if z-star is bigger than 2.326, we can reject the hope. We can support the hop. I did not just write 2 things. I wrote 1 thing. If it looks like this dude is wrong, it automatically also means this dude looks to be right. Those aren't 2 separate things. That's the same situation. Everybody with me? If I can reject this dude, that inherently means I support this dude because they are opposites. And maybe. I used to call this 2 old men arguing in a coffee shop. Right? I don't know if you guys ever seen, you go to a coffee shop and there's always old people with a newspaper in there. I don't think this is right. Well, you're stupid. No? Okay. I was grade in places and I always see this. So maybe I see why I stopped calling it 2 old men in a coffee shop. Okay. Okay. So, what are we talking about? What are we allowed to use to talk about it? What's enough evidence? Did we get enough evidence? That's the first 4 steps. And of course, the 5th step is going to be your favorite, writing the conclusion. So this step is old news. Can anyone tell me from the information I gave, what is X bar?
It is 12.45.
12.45, 11. Does everybody agree? Okay, because Edmundo and I could both go insane. You never know. So we've got to make sure we're not, hopefully. What's sigma?
4.27.
4.27. I love it. Make sure you can find that. What is the new standard deviation?
2.2.
And why do I have to do that? Because this is all about sample means, and I took a sample. So 4.27 divided by the square root of?
Square root of
41. So somebody help me out. Let's see, what is that? Bum, 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 bum. Oh, neat. Jeff's hidden messages here about. What do you guys get?
0.669.
669? Did I do something wrong? 427 divided by square root of 41. I get 0.66686. So 667. Okay.
Oh wait, yeah, 667.
Okay. Oh, I see what you're looking at. Yeah, too many sixes get all jumbled. And now I can calculate the z-score. So I just call the z-score that we calculate from the sample, I just call it z star. Just to differentiate it from the z-score that I already have here, right? So z star is always the same formula. It's our data, 12.45, minus what we're assuming the middle to be, 10.15, divided by the standard deviation, 0.667. Is that 2.3? 3.45?
$3.448.
Okay. Let me stop for a minute. You guys all get that? So same old formula. It's the same old formula. The one thing I want you to realize, I kind of snuck it in there real quick. We go into this assuming this number is the real mean. We assume it's the real mean, and what we're doing is we're looking for a contradiction. So we're like, okay, assuming it is 10.15. Look what we just did. Well, what did we just do? Where is this on the picture? 3.45. Where is it?
Very far out.
Way up here, right? So I can put a little star in it. That's another reason I call it Z star. Ooh, Jeff. Did we make it far enough away?
Yes.
Yes, we made it far enough away in order to be able to say what? We made it in here. What does that mean? What can we do?
The hose wrong.
Yeah, we have it right here, don't we? We can reject the hope. We can support the ha. So again, we have, what are we talking about? What are we allowed to use to talk about it, to analyze it? What's enough evidence? Did we get enough evidence? And then conclusion, right? So there's nothing really new in here except for a symbol or two and the idea of the alternate and null hypothesis. Everything else is like old news. This, though, when you hear somebody say on TV, it's been clinically proven, blah, 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 that hasn't been proven worth shit. They found good evidence. So I hate when they say it's clinically proven. No, they found enough evidence they got far in that full way. So like in a trial for a new drug, the null hypothesis would be it doesn't affect, it's zero difference from the old drug. So the alternate would be it's improved, right? So you just find, you take a sample, you give this sample the new drug, you give this sample the old drug, and of course you have a control group sometimes. And you just gotta show, yeah, the difference is big enough. So they shouldn't say proven. They should never say proven because you can't prove shit. You can show really good evidence. If you are found not guilty, does that mean you're innocent? No. Hell no. It just means they didn't find enough evidence. Now again, it doesn't mean you're not innocent. We just don't know. We just couldn't find enough evidence. Did we find enough evidence? Yes, we made it way the hell out here. We found enough evidence to say. So if the null was innocent, we found enough evidence to say it's guilty. Now, is there a chance we're wrong?
Yeah.
What's the probability we're wrong? 1% chance. Which in general is good, but it still means we could, 1 out of 100 times, we could be wrong. So here's how the conclusion works, and then I'm going to let us out because this is a long ass day with this business. What is your conclusion? So let me ask you this. The way this works, if I was a consultant, a statistical consultant, somebody would come to me with a claim and I would go test their claim. When I come back to them, don't they want to hear if their claim is good or not? So when we write a conclusion, it's got to reference the claim. Remind me, was it the ho or the ha? Which one of those was the claim?
The har.
Which one?
Ha.
The ha was the claim in this case. It won't always be. You guys see that? Here's the claim. It's the ha. So which language do I want to use then? If I want to talk about the claim, this language. Because this last, and again, obviously, we're going to do a shit ton of more examples, right? So don't feel like you're supposed to understand everything in the universe. But when people write the conclusion, they're always like, how do I know what to write? That's it. What we just did. What's the claim? Then you know exactly which one of the, if the claim would have been the ho, I would have used this language. So how do I write this? We support the ha. So do we find evidence? Yes. We have found sufficient evidence to support the claim that plagiarize. There's one time you can plagiarize. What exactly is the claim? Northern Minnesota coyotes live longer if they're given more room. Okay. Northern Minnesota coyotes, that looks like New Mexico, but I don't care. Northern Minnesota coyotes live longer in captivity if given more room. Now that is a statement of a conclusion that makes immediate sense. If somebody made a claim, I think they live longer, this is what they want to hear from me, something referencing their claim. We have found sufficient evidence to support the claim that they live longer. So we've got good evidence that they do live longer. What would that mean should happen? They should be given more room. Everywhere across the United States, they should be given more room. And if they can't be, they should probably be released or something, or maybe not released because the poor things probably don't know how to fend for themselves. But they should just be given more room. Yeah.
Question.
Yeah.
How can we tell it's one or two tail?
Ah, beautiful. If the claim would have been, if a researcher believed that the northern Minnesota coyotes live, how would I say it in this? He said he believes that it isn't 10.15 years. He thinks it isn't 10.15 years, right? So if you thought, no, they don't live 10.15 years, what does that mean? They could live longer or shorter lives, yes.
So if you see it isn't or no,
Yeah.
you automatically think.
Shoot, I should have brought that. Well, I knew we wouldn't probably have time. If I said, let's try this. Let's do one quick example that shows some of the other things, and then we'll head out. If I had a claim and I said, I think the average grade in here is a 75. So what's the claim that's being made?
It is 75.
Mu is 75, right? Would that be the ho or the ha? What's the key thing about the ho? It has to have an equal sign. So this is the beauty. I want you to understand. You can write the claim. The claim should be really easy to get. And then you just step back. Does it have an equal sign or does it not? This one explicitly has an equal sign, right? So it's got to go here. What's the opposite of this?
Does not.
The way we used to write does not equal to was like this. I'm kind of happy we stopped because math people don't like multiple symbols in a row like this. But do you see how to write mu less than or greater than? But to be not equal to, where would it have to show up to show evidence that it's not equal to? Up here or down there? So not equal to is a little less committed, right? You're like, it's not 75. You think it's greater, less than? It's one of those things. So that's a two-tailed test. You guys with me?
So on simple things like that question, automatically assumes like equal then kind of in a way?
Well, is.
Oh. Okay.
I think that, okay, that's a claim.
Okay.
The average grade is a 75.
Okay.
So this would be the claim since it has an equal sign. There you go. What if I said is at most 75?
And you're saying it is less than or equal to.
Yes, at most means up to, right? So less than or equal to. Where would that go?
Still be that.
In the ho, because it's got an equal sign in it, right? So it'd be here. What's the opposite of that?
Greater than.
What? How many tail tests would it be? One tail up here. Now again, I know this is all new, and I know you don't quite feel comfortable with this, but I'm trying to show you it's not going to be as hard as it would originally seem. And again, we just did one problem. Why did it take so long? Because I explained each step, right? So we're going to do more examples next time, and just kind of do more examples until you go a little crazy, if you aren't already crazy. And of course, we're going to get into, there will be problems where you have to use t-scores, but not much is going to change. We just use the t-score chart to look at the t-scores. There will be problems with percentages. And that one we have to do a little work to figure out what the z-score formula is going to be for percentages. We have to create that. But the steps would stay the same. Okay, I think that's plenty.
What's the section of the homework for chapter 9? Are we able
Yeah,
to-
oh, I always forget. So many things I forget about this book. Chapter 9, they don't give you a complete hypothesis problem until section 9.5. 9.1, 9.2, 9.3, 9.4, they each focus on one piece of this. So they're like very specific questions. 9.5, you get the entire thing you've got to do.
So,
And by the way, real quick, the book references a worksheet in the back of the book. Screw that worksheet. You do those 5 steps. Their worksheet assumes you're going to do all the work in the calculator, which we're not going to do that. So don't use their worksheet. Use the 5 steps here.
so do like section 9.1 or?
Yeah, you could. Yeah, 9.1 focuses on the null hypothesis alternate. It also has types of errors, which